Hi there. In this video, we're going to be talking most specifically about the equation of a line in space. But we're also going to spend a little bit of time talking about curves and surfaces and the difference. And if you remember from the getting started or the class overview video, that has to do with dimensionality and a term called degrees of freedom. And this video kind of goes with the next video, which will cover the equation of a plane in space. And the distinction is important, and it all has to do with dimensionality. And what we'll basically be doing is looking at the most basic type of curve, which is a line, and then looking at the most basic type of surface, which is a plane. And again, just talking about how to get equations that describe them. All right, so here we go. Okay, so you might want to recheck that class overview video if you've forgotten some of this stuff. But if you remember from that video, we brought up the point that a curve is one-dimensional, no matter how many dimensions it's drawn in. So we can draw curves in 2 dimensions or in 3 dimensions, and theoretically in any dimension. But as far as the curve itself, it's a one-dimensional object. And what that means equation-wise is it only has one independent variable. All right, and in some other kind of jargon, we say that there's 1 degree of freedom. Remember what it means to be an independent variable. It means you're free to choose values of that variable, and then it determines everything else. All right, and so we have 1 degree of freedom in that case. All right, and so remember the idea of a curve. A line is a curve, okay, but I could be drawing that line in space, all right, like that. But also a curve can be twisted, and we'll talk about those kind of curves later. But regardless of this, to get equations of anything that's one-dimensional, a curve, there will only be 1 independent variable. So that kind of helps guide you about how to set up equations, especially whenever you do problems or take a test or something. It helps avoid silly mistakes. Okay, surfaces are 2-dimensional, and so what that means is there's 2 independent variables. And so likewise, since we have 2 free choices, there's 2 degrees of freedom. Okay, and so the most basic surface is a plane. You know, we usually think about planes as being infinite, but I usually draw them cut off so that we can actually see them. All right, but they can also be curved, and so here's a very basic looking surface right here. And just remember the idea of a surface, it's actually composed of an infinite number of curves all kind of glued together. All right, so in this video we'll be talking about the most basic type of curve, which is a line, and then in the next video we'll be talking about the most basic type of surface, which is a plane. All right, so you might want to read this question and pause it after I explain. So about the equation of a line in 2D. So this is back when we've been graphing in the XY plane all these years by this point. All right, ask yourself, to get the equation of a line, what do you need to know? Okay, and maybe pause and think about that. I'm going to go ahead and move on though, so please pause if you're going to pause. But I get all kinds of different answers, and the key thing is if you think about it, we usually end up getting it in this form right here. Okay, and so that starts giving you a hint. Remember, we need to know these 2 numbers. So a few answers I'll get whenever I ask this question in class. Some people will say you need 2 points, and 2 points is one way to get the equation of a line, but we don't necessarily need 2 points. And you can kind of see right here, you need to know the slope. Now I'll have people half answer this correct. They'll say, well, you need m and b, so you need the slope and the y-intercept. You don't necessarily need the y-intercept though, because if you're given a point, another point, you can plug them in here and solve for b. Or some people know the more general equation of a line. It's called the point slope form that looks like this, and that's the one that I use. And so this form really illustrates what you need. You need the slope, m, and a point on the line. Okay, and that's what that x naught, y naught is denoting. Okay, now why do we need those 2 things? Okay, and so let me point out 2 things. Say I just give you a point that has to be on that line, x naught, y naught, like that. So you know this point has to be on the line, But how many lines pass through that point? Well, there's this line, there's this line, and there's this line, okay? And there's an infinite number of lines, right? Okay, so we need that slope to tell us how that line is inclined, okay? And just the opposite, say that I just told you the slope, okay? Well, let's say the slope looks like something like 2 over 1, okay? Sorry, 2 over 1. So one line that has that slope is this line right here, okay? But then any line that's parallel has that same slope. So I need that point to fix the location of where that line's going to be. And so that's why I need these two things right here, okay? And there's a nice thing that'll help you understand the three-dimensional analog of this, is that the slope gives the direction. Okay, in 2D, you can express direction just by the way that thing's tilted. Okay, the problem is, try to visualize a line in space. Okay, to try to describe the way that thing is tilted depends on the way you're looking at it. And you could actually think about there's actually two slopes: the change in z over the change in x, or the change in z over the change in y. There's also a third one, the change in y over x. Okay, and so we'll need something different. There's not a clear slope in 3 dimensions. But the key thing to understand about what the slope is giving us in 2 dimensions, it gives us the direction that that line is pointed in, okay, or is traveling in. All right, and then that point x naught, y naught, that gives the location, or it fixes the location is what I should say, of that line, okay? And so whenever we give them both, we exhaust these impossibilities. And so like in that second picture with all those parallel lines, if I told you that the line also had to pass through this point, then I know the line that I'm looking for is this single line right here. All right, and now these ideas will carry over to 3D, but like I say, there's not really the idea of a slope, or the slope, I should say. There's several slopes we can compute, but there's not just a single slope. But it's this idea. All right. In general, to get the equation of a line, we need to know what direction it's traveling in, and then we use a point to fix its location. Okay, and we almost got the whole story put together here, except the derivation of the form of the lines is very different than what you're used to seeing as well. But anyway, to get the equation of a line in 3D, we need a point on the line. We need to know at least one point that's on the line, okay? And that fixes the location of that line. But we need to know its direction also, okay? Now, what could we use to specify a line's direction? Think about that, and in terms of things we've been talking about, it might be somewhat obvious. What tools have we been using to specify a direction? And that would be a vector. Okay, and so what we really need is we need to know a vector that's parallel to the line. Okay, and in general we'll just call that vector v. All right, now let's make sure graphically that this will work out, that if I just specify those two things, then I should be able to determine a line. Now for now we don't know how to get the equation, but by determine we should be able to draw that line uniquely. Okay, so say I tell you that this line needs to be parallel, the line that I'm looking for needs to be parallel to this vector right here. All right, and then it also passes through this point right here. And the question is there only one line that does that? Okay, and so I can draw the obvious line. That would be this line right here. All right. Is there another line I could draw that has those same properties, that it passes through this point and that it's parallel to this vector right here? And the answer is no. Okay. There's no other line that's parallel to this vector and also passes through that point. And so that's the key thing. These are the two things that will uniquely determine a line in space. All right, and so one thing about getting equations of any kind of object, whether you're talking about the equation of a line in 2D, a circle, or a plane, or anything, is to always get started, know what you need. Okay, it's so easy to spend time doing work that leads nowhere. So anytime we're talking about the equation of a line in 3 dimensions, hopefully in your brain just boom, I need a point, I need a parallel vector. Okay, and those are the two things. Now we'll see how to actually derive the equation from that. Now, before we get to the actual equation of a line, there's some verbiage and notation that you need to be aware of. Okay, so if you remember the idea, this doesn't matter if we're in 2D or 3D. So first I'm just going to draw in 2D. All right, so remember there's a distinction between this point x naught, y naught, which only gives you a location, and the vector that starts at the origin and goes to that point. Those are really two very different things. A vector is an actual quantity with a direction, whereas a point is just a location. But there's a natural correspondence between the two things. All right, and so what we do is sometimes especially in a topic called linear algebra, a lot of times we're trying to talk about things that we can do to just points, but we'll use vectors to describe them because we can take advantage of vector operations. If you think about it, there's no way to multiply 2 points, okay? But there are 2 ways to multiply vectors: dot product and cross product. Same thing with points. You can't add points. It doesn't make sense to like add Paris plus London. You know, those are locations with point coordinates. But it does make sense to add and subtract 2 vectors. Okay, so for that reason, we use something called a position vector. Okay, and so if I call this point P right here, but if I want to talk about the vector that goes from the origin to this point right here, we call that the position vector, and we usually use the letter R to denote it. Okay, so this vector right here, we might just call it R. All right, if we're talking about a general point, we'll use the letter R, but if we're talking about a specific point with subscripts, we'll give that the corresponding subscript, like that, okay? But if we're just talking about a general point in space, okay, so you know in math we often talk about just like some general quantity to illustrate a property. So if we're just talking about a general point in space, and so that would be the point x, y, z, then we will denote its position vector just with the letter R, okay, like that. All right, now in space what this would look like is you have this point x, y, z in space, like that, so its position vector would start at the origin and go out to that point. Now I might have a specific point x naught, y naught, z naught too. Okay, and we are. The reason I'm bringing this up, we're going to use 2 position vectors to get the equation of a line. So I might have this other point, x naught, y naught, and z naught, like that, a specific fixed point. And so its position vector would go from the origin out to that point. So this vector would be r naught, like that, and this vector right here would just be r. Now, one thing, you can pause right now and think about it. I'm going to explain this in a minute, but this is something we're going to use in a minute. You might want to pause and ask yourself, if I draw this vector right here, what vector is that? Can I describe that vector right there in terms of these 2 vectors right here? I'll leave that up to you whether you want to pause and think about that, but now we're ready to develop the equation of a line. Okay, so what we want the equation of a line in 3 dimensions given a point on the line, so this point right here is on the line, and a vector parallel to the line v. So we're given these 2 things, okay? And so I'm just going to draw a general v and point, all right? And so say our parallel vector looks like this. Assume that it's kind of going into the screen a little bit, all right? And then we have this point x naught, y naught, z naught. So say the line has to pass through this point right here. Okay, like that. So we can see what this line looks like, right? I'm going to draw it in white just so I can write over it in a minute and you'll be able to see it. So there's a pretty good idea about what that line looks like. Okay, so here's our point. Okay, now one thing to point out is I can draw the position vector to my point. Okay, so I'm going to draw its position vector. And since we're talking about that specific subscripted point, I would call that R naught. Okay, now here's the thing, and this is one place where people get confused about what does it mean to find the equation of a something. That means that I should be able to talk about some other point that's on the line and get some kind of equation that gives x, y, and z in terms of what I'm given. So I should get some equation or equations that involve x, y, and z that can be described from this vector and this point, and that has this corresponding position vector. Now I realized as I was pointing, I forgot to label something. So here's that parallel vector v. Okay, so that's the idea about getting the equation, is I should be able to get some equation or equations that give that tell me how to determine this point x, y, and z from everything that I'm given. Okay, so here's the idea. So I want to talk about how to derive this point, okay, or any other point on the line, but I just drew a general one. Okay, so make sure you realize this vector right here has a position vector. Okay, and so let's draw its position vector like that. Okay, so there's that. And so since that point's not subscripted, we would just call that vector R. Okay, like that. Now, if you noted, like I pointed out in the last slide, there's going to be this new vector that we can draw in. Okay, I need a different color now. And so there's going to be this new vector drawn in that I can draw that starts at our R naught point and extends to our R point. So this vector right here. Okay, now we got to think about this. This is the vector that so notice right here, these two vectors, the two position vectors, are drawn with the same tail. So in a sense, I'm going to erase this just or my picture's starting to get a little crowded. But if you think about it, we have our parallelogram right here that's determined by those two vectors, right? Like that. And I've drawn a vector that goes along one diagonal of that parallelogram. So that's either a sum or a difference. But if you remember, the sum goes from their common tail to the other diagonal. So this vector has to do with their difference. And remember, the difference starts at the second vector and extends to the first vector in the subtraction. Okay, let me see if I can get those lines out of there. Yeah. Okay, the parallelogram I'm talking about. All right, so that yellow vector, I'm kind of colorblind. I don't even know if that yellow vector is yellow. It could be oranges. But this vector right here that I've drawn, I need to go to a darker color so you can see it. But that vector right there is actually R minus R naught. Okay, now what else is significant about that vector? Look at this vector right here. Okay, and look at our given vector v. They're parallel to each other. Since v is parallel to the line and this R minus R naught is on the line, these two things have to be parallel to each other. Okay, and that ends up being the key to getting the equation, is that R minus R naught, the vector R minus R naught, is parallel to the vector v. Okay, like that. Well, what does it mean to be parallel in terms of vectors? That just means that it is a scalar multiple. I don't know if you see the beauty of what's coming up now, but we're actually ready for the first form of our equation. This is a general equation. To get a specific one, we would have to know specific numbers. But what we can say is that R minus R naught is a scalar multiple. Now, you're used to using C or K as a scalar multiple, but we're going to use the letter T for it. All right, and so is equal to T times V. All right, now what's key about this, first of all, I can solve this equation for R. So I would get R naught plus TV. All right, like that. And this is called the vector form of the equation of a line. We're going to look at it more specifically too, but this is the first version of the equation of a line in space, and so this is called the vector form. Now this looks very abstract, but make sure you realize, how would you generate other points on the line? Okay, this point right here is one specific value of t. Okay, these two look close to the same size, so, and they're pointing in the same direction, so t for this point right here might be something like 1.3, just a little bit bigger than our vector v. Okay, but to generate another point on that line, then I would make up another value of t, and what it would do, say I used t equals 2, all right, I would start at r naught, and I would draw a vector twice as long as v along that line, so it would end up somewhere out here. Okay, if I plugged in -1 for t, then what's going to happen? -1 times a vector just reverses the direction. So I would start at my r naught and just redraw v going in the opposite direction. So I would end up with the point on the line over here. So that's actually how you generate different points on the line. And so hopefully you see we've completely accomplished our goal. We can generate any point on this line right here just from knowing the initial point that's on the line and a parallel vector. And so that's the idea of getting the equation of some object, whether it be a line or a curve or a surface. All right. One other thing too that this is a good point since we were talking about it. Make sure you realize whenever you plug in positive values of t, you generate points to from r naught that are in the direction of v. So this side of the line gives you or is obtained from using positive values of t. Then if I plug in negative values of t, I get points on this side of the line. Now just don't oversimplify that. Sometimes the parallel vector points in the other direction. So, but the key thing is positive values of t generate points in the same direction as v. Negative values of t generate points in the opposite direction of v. So just to show you what I'm talking about here, here's what I was trying to draw right here. So here's my point P, my point P naught. Okay, so that's that x naught, y naught, z naught I was talking about. Here's its position vector, this r naught. Okay, and here's the line or the vector that is parallel to my line. So first of all, realize that determines that line. So that line would have to be positioned right there. Okay, notice it's parallel. All right, and then the way we generate points on that line is I take that vector equation and then I plug in different values of t. I call this t sub p for my point P on the line. So right now t sub p is equal to 0. So that means it's starting out at that given point, that p naught. But then notice that if I change that t to 1, like there, then it generates this new point P, and its position vector is r. Okay, and so as I manipulate the value of t, I get different points along that line, and it's very key to make sure, because of that equation, we're guaranteed to get points just on that line. Notice that those are all positive values of t. So then if I use negative values of t, then I get points in the other direction from p naught. Okay, so that's how that equation works, and I hope that helps you understand a little better. Okay, now this is a good equation to work with, but I admit it can be a little bit abstract, and so there's another form of the equations called the parametric form. All right, and that also gives you the line. It actually ends up being 3 different equations though. And what we can do is we can write things out here in terms of our components. So remember, r was the position vector for that general vector. So that would just be the vector with coordinates x, y, and z. All right, and then r naught was the position vector for our given point. So it has coordinates x naught, y naught, and z naught. Okay, and then remember we let t vary, so that's going to be the variable, the independent variable for the line. And then we get the coordinates for our parallel vector, although we haven't looked at a specific example yet. that would be the form of it right there. Okay, the general form. All right, now notice over here on the right side, the first thing I have is a scalar multiple times a vector, so I could distribute that inside, and then I could add those two vectors together. All right, I'm going to do both of those at once, and so we get x, y, z, and then whenever we add the two vectors together, we'll add their first components. So that'll be x naught plus t times v1. So we get plus t times v1. Okay, and then in the second component, we'll get y naught plus t times v2. And then in my third component, I get z naught plus t times v3. Okay, like that. And so now what do we have? We have two equivalent vectors. We're saying one vector is equal to another vector. That means that each one of their components have to equal each other. So we end up getting three equations here. So if we equate the first components, we get x is equal to x naught plus tv1. And then we get y is equal to y naught plus tv2. And the third one is called, it says that z is equal to z naught plus t times v3. Okay, and this is called the parametric form of the lines equation. All right, like that. Now, make sure you realize what it's given you is that, remember, t is the independent variable. T is what allows us to generate different points. Okay, and so this is our variable. And if I plug a value in for t, what does it give me? We calculate each one of these things, and it gives me the x, y, z coordinate of that point on the line. Okay, like that. All right, one thing I should have even mentioned before. Remember, we're graphing a curve. The most basic type of curve is a line. All right, and curves are one-dimensional, so they should just have one independent variable. Make sure you realize no matter what form of the equation we're in, we do have that. These are like constants. They're constant vectors that are given to us. So there's only one number to plug in. That's 1 degree of freedom, or one dimension. And so we see that here. The parametric form looks a little bit strange because we do it, but notice that we do only have one independent variable. After we plug that t in, we get three different independent variables, but they all just depend on t. Okay, and so that's the way that works. Now let's look at some concrete examples to see this in action. One thing too, I just thought to mention. I'm surprised I didn't think earlier. Is in the vector form. Notice that we have have this like that, and I could rewrite that. It doesn't matter what order we write things in. So we have that, right? Okay, why am I pointing this out? I want to show you the similarity to the two-dimensional equation. In two dimensions, we think about the equation of a line looking like y equals mx plus b. Okay, think about what these things give you. M gives you the direction, and b gives you the y-intercept, but that's just a point on the line. So this is just a point on the line, and this is the direction. This gives you the direction. Same thing here. Now our variables are a little bit, let me rewrite that too. I could rewrite that t times v as v times t, right? Like that, okay? And so notice its similarity. We have m. M was given us direction. Now v was given us direction. T is our independent variable, okay? And so that's like the x, all right? And then plus the r naught is a point on the line, so that's kind of like the b. So they kind of have the same form. I know it's not, doesn't perfectly line up, but I'm just showing you the similarity. All right, so let's look at an actual example. This one's pretty basic, just making sure we know how to plug into the equation. All right, and so a line passes through the point 1, 3, 5 and is parallel to the vector negative 2, 4, 1, and we want to find the vector and parametric equations for that line. Okay, the key thing is, now this is good by the time you get to a test or just out there in practice in general, we're finding the equations for a line, and this line is in space. Okay, so automatically, hopefully in your brain, you can get to the point to know what you need. Okay, and what we need is we need a point and a parallel vector. Okay, like that. All right, and notice we're given both of them here. And so the point we want is 1, 3, 5, like that. And the parallel vector is negative 2, 4, and 1, like that. Okay, now in terms of the vector form of the line, then its general form is r equals r naught plus t times v. All right, so remember what r naught is. It's the position vector for your given point. So all it involves is rewriting this as a vector. Okay, and so we have r is equal to the vector 1, 3, 5, and then plus t times v. We already know v. It's negative 2, 4, 1. Okay, like that. And that's the vector form. You could go ahead and work it out a little bit more. It'll save you time for the parametric equations anyway. And so remember what the idea is. I can distribute the t and then add these two vectors together. And so this is 1 minus 2t, comma, 3 plus 4t, comma, 5 plus 1t, or just t, like that. All right, and you can see the two forms of the equation are just basically different ways of saying the same thing. They're highly related to each other once you actually do an example and see it. Now, one thing to point out, if you actually wanted to get points on that line, you would just make up different values of t there, and for each value of t, it's going to give you a vector. That's the position vector for a point. So then if you actually wanted to write the point, you would convert it to point form. So just as an example here of doing that, say I plugged in t equal to 1, then that would give me that r is, what is that, 1 minus 2, which is negative 1, 3 plus 4 is 7, and then 5 plus 1 is 6. And so what that's saying is that the point, negative 1, 7, 6, is on the line. Okay, now in terms of getting the parametric form, all you're doing is setting each one of those components to x, y, and z successfully. So all the parametric form is saying that x is equal to the first component, 1 minus 2t, y is equal to the second component, 3 plus 4t, and z is equal to the third component, which is 5 plus t. Now if you wanted another point, let's do t equals negative 2 there, okay? Then in this form you would just say x is equal to 1 minus 2 times negative 2. That's going to give you 5. Y is equal to 3 plus 4 times negative 2. That's going to be negative 5. And z is equal to 5 plus negative 2. That's going to be 3. And so there's a way to get another point on the line, like that. Okay, so and so there we go. Okay, the most common type of situation to have in finding the equation of a line is you have 2 points and you want to connect those two. All right, and so we have the idea here. This is just going to be a rough sketch, but here's 1, 2, and then up 3. Here's our first point, and then we have 5, negative 2, so we're going to go back here on the negative y-axis 2 units, and then up 1. So we roughly have this line right here. I know it's not the best picture, but our line basically looks like this in some sense. Okay, like that. So anyway, we're trying to find the equation of the line. We'll give both forms. I didn't write it out as explicitly as the last example. But so to get the equation of a line, the key thing is you're getting the equation of a line. Know what you need. All right. And so what do we need? I should have said question mark. We need a point on the line. Now we're given 2. All right. Remember this from algebra. If we have 2 but we only need 1, you could just pick either one. I usually try to pick the simpler looking one. Okay. The trickier part on this is we need a parallel vector, which isn't given to us. Okay. So how could we get a parallel vector? Well, if you think about it, you might want to pause real quick and see if you can beat me to it. But if you think about it, if I draw the vector starting at at one point and going to the other point, I'm going to draw it going this way because that's at 1, 2, 3. All right, then that vector is definitely parallel. Now, what you might be confused about, because we're drawing that vector on the line, but if you think about it, we can redraw it starting at the origin, right? And so than the way we were drawing it before. We would just draw the same vector, just starting at the origin. Okay, so let me label those 2 points just to kind of help you understand what I'm doing. So let's call that first point P and this second point Q. Then our vector V is going to be the vector that starts at P and extends to Q. With that, how do you get the components of that? You do the tip minus the tail. All right. So we subtract the x coordinates, that would be 5 minus 1, which is 4. And then I subtract the y coordinates, which is negative 2 minus 2. And so negative 2 minus 2 is negative 4. And then I do 1 minus 3. That's going to be negative 2. Okay, now this could be our parallel vector, 4, 4, negative 2. But notice I could factor out a 2 from that and get 2, 2, negative 1. And all we're looking for is any vector that's parallel to the line. And notice this vector right here is a little bit simpler than that vector right there. So I'm going to use that. I like to keep things simple. You don't have to. And that brings up an important point. For the equation of a line, there's not the equation of a line because we just need any parallel vector. So I could just as easily use v is equal to multiply that by 5 and use 10, 10, and negative 5 like that. So that can give you different versions of the equation of a line depending on what you use as your parallel vector. Also, I'm using this as my point P naught, but I could just as easily use that one. So that's a little tough to answer equation of line questions because of the fact that we can use different vectors or points. But anyway, once we're there, now we have our point, 1, 2, and 3, and we have our parallel vector. So this is going to be our P naught here. We have our parallel vector, 2, 2, negative 1, like that. So we're ready to plug in to our equation. And so we could say R of t is equal to R plus t times v, which would be, R naught plus t times v. So that's going to be our point written as a vector, the position vector, and then plus t times 2, 2, negative 1, like that. And then I go and distribute and add. I'm going to get 1 plus 2t and 2 plus 2t, and then 3 minus t. And that's going to be the equation of my line in vector form. And I prefer that form. If you wanted to write it parametrically, you would just say x is 1 plus 2t, y is 2 plus 2t, and z is 3 minus t. A couple small subtle points too. Notice that I wrote my equation in the vector form in this case as r of t. So sometimes we want to stress that curve depends on our value of t, just like with function notation. Sometimes we just write r equals. Sometimes we write r of t equals. So that's just kind of up to you, but just some notation. Now, one thing about the values of t, if you're going to generate points, since I made the vector that goes from P to Q, this vector is pointing this way. You can see the arrow right there. Okay, and so if I plug in positive values of t to generate points, I'm going to get, here's my initial point, my P naught. So if I plug in positive values of t, I'm going to get values of t that go this way. If I plug in negative values of t, I'm going to get points that go this way from my initial point. All right, and then the other thing is just to remember, since we can arbitrarily pick which point we want to be our initial point, and we can get different forms of that parallel vector, the actually way that we write the equation of a line isn't necessarily unique. We could get one graph for different types of equations depending on what we used. Okay, so I'm going to leave it there for now. Those are just some basic examples of getting an equation. You'll probably see some trickier ones in the homework and test. And so the key thing is just to focus on what you need. Notice the question, equation of a line. And so you just focus on what you need to find. You need to know a point on the line, and you need a parallel vector. And then you can just fill in. Once you found those, you just fill into those forms. So make sure to focus all your work. And then just be aware that mostly what we're going to do, we're getting this down, but then we're going to use this idea to find special types of lines. If you remember, there's the tangent line to a curve. And so we'll be doing that in space and so on like that. Okay, so I hope that helps, and I wish you the best.